Hey there, welcome back to the channel, and this is CSES problem solving sessions. And so today in this video lecture, we're going to be solving the next problem in the session. So that is shortest routes, shortest routes one. This problem we're going to be solving in this video, and this problem is a simple one. And if you know how to find shortest path, if you have ever solved a problem related to Dastra algorithm, single source shortest path, you must have learned about Dastra algorithm, even if uh, in your course as well. So if you are BTech student, you must have learned about Dastra algorithm, है ना? Dastra algorithm appears in data structures and algorithms, as well as it appears in computer networks as well. So this is a very common and standard algorithm for finding the single source shortest path. Starting from a single source, you can find the shortest path to the rest of the vertices in a graph. Now the graph can be the network of cities, it can be the network of routers, it can be the uh, you know maybe network of mobile phones, right? Network of cities, network of islands, network of countries, etc, 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 right? So but you should understand, we should understand in this video lecture the underlying technique, how to like the Hey there, welcome back. So this is your Ramandeep Singh, and today we're going to be solving the next problem in the CSES Graph Algorithms section. And the problem that we're going to be solving today is this shortest routes two. Now you may have noticed that I have skipped this problem shortest routes one, just because I have already solved that problem in a video, and the video is present over my YouTube channel. I'll upload that to the website, and here for this particular video I'm going to solve this shortest routes 2. Now shortest routes 1 is basically based on Dastra algorithm, and it's just a plain implementation of Dastra algorithm, that's all. Single source shortest path. But here this problem is a little bit different. Let's see how we're going to solve this problem. So in this video we'll be focusing entirely on this particular problem, that is shortest routes 2. So there are n cities and m roads between them, right? So we have been given n cities and there are m roads between them. Your task is to process q queries where you have to determine the length of the shortest route between two given cities, right? So you have a n cities and m roads between them, and now you have some pairs of cities. How many pairs? Q pairs. So each pair is like a comma b, and you need to find the shortest route between a and b, right? That's all you have to do. So you have to print q integers. Each integers represents the length of the shortest route between a and b, right? That's what you have to do. And now there may be some case when there is no route between two nodes given a and b, and in that case you will print -1. Cool, eh? Now let's jump to the code of this not code, of course, sorry. Let's jump to the solution of this problem. So let's see how we're going to solve this problem. Let's take this example. So let me copy paste it. So here we have a copy paste example for that, and from here what I'm going to do is I'm going to let's build a graph. So we have n, m and q. N is 4, m is 3 and q is 5. So n is 4 means we have 4 nodes, 1 2 3 4, right? Then we have 3 connections between them, right? So the first connection is this 1 and here 2, 1 and 3. Then from 2 and then there is a connection from 2 and 3. So there is so there is a connection between 1 and 2, then between 1 and 3, then between 2 and 3. So the weight for the connection 1 and 2 is 5, right? That's the weight from 1 and 2. Now what's the weight between 1 and 3? Between 1 and 3 the weight is 9. The weight between 2 and 3 is 3. So these are the weights that we have. Now what you need to do is you need to answer Q queries. So we have 5 queries. The first query is the shortest path between 1 and 2. That's obvious in this, from this diagram. The shortest path between 1 and 2 is of length 5. The shortest path between 2 and 1 is also 5. From 2 to 1, this path, direct edge. We have a direct edge from 2 to 1. Now this is an undirected graph. So we have an edge from 1 to 2 and we have an edge from 2 to 1 as well. Then we need to find the shortest path from 1 to 3. Now first path is this, the direct edge. There is a direct edge between 1 and 3 and that has a cost of 9, versus there is a indirect route from 1 to 3, that is move from 1 to 2, then from 2 to 3, giving us a total cost of 5 plus 3, that is 8. So which one is better? Of course 8 is better because it has shortest cost, not shortest cost, lower cost, right? And lowest cost, or we can say the shortest length. Now the distance that we have to cover while we start from 1, then move to 2, then eventually move to 3 is of 8, right? Then we have 1, 4. We want to find the distance between 1 and 4. Now I can see that there is no edge, there is no route. We don't find any connection from 1 and 4. Have you? I don't see any connection from 1 and 4. Like there are 4 lies entirely in the another connected component and not in the connected component where 1 lies. So there is no path from 1 to 4, and for this particular query the answer would be -1. What's the answer for the next query? That is from 3 to 2. Now from 3 to 2 we have a direct edge and the length of the edge is 3, and this is the best answer that we can have from 3 to 2. Why? Because if we go through the alternatives, that is if I move through 1, so I move from 3 to 1 and then from 1 to 2, right? So instead of, so what's the battle here? The battle is between moving from 3 to 2 directly versus moving from 3 to 1 then from 1 to 4. So now for this particular thing, the first way, the cost is of unit 3, right? So we'll also write the costs as well. So for this the cost is 3 versus the cost for 312 would be 9 plus 5, that is 14. So 3 versus 4, obviously 3 wins, so the answer is 3 here, if I am not wrong, right? Now that's fine. Now is there anything else? No. So these are the answers for the first test case that has been given to us. The CSES usually gives only one test case. You can see that there is only one test case. You should be able to think of test cases by yourself. So if you're solving these problems and you are here, I'm sure that you have good introduction to the basic or fundamentals of problem solving and programming. You know what are test cases, how to generate test cases, you know how to think of test cases, how to think of edge cases, you people know about it. What is TLE? Why do we encounter TLE? What is MLE? Why do we encounter MLE? Right? what is what with the stack overflow, right? These type of errors you have, segmentation faults, you people are aware of these things, you know. Now here, uh, the thing to be taken care of here is you people should be able to draw such examples by yourselves. Now we have only one example here. You should be able to think of more such examples by yourself. So before, if you do not understand this thing well, then you can draw, you can try out this thing, you can try out these queries, take a piece of paper, draw such graphs, larger graphs of 10 nodes, 15 nodes, and give some queries, and then just use pen and paper and try to understand what the question is actually asking. That's the process, right? That's the process, and there is no alternative to going through the process. You have to go through the process, you have to face things, and you have to, you have to make your mind disciplined. And yeah, of course, this may be a pain, but the saying is, no pain no gain, and also there is a joy in the pain. That doesn't mean that you should, like, deliberately give yourself pain, but actually when you are going through some, these type of self improvement activities, you're learning something. Learning is not easy, if you are really learning, that thing is hard. But there is a joy when you learn something, when you become better every day, when you become capable of doing some task which you were not capable, right? So let's say, 1 month back I was not able to solve this problem. Now after 1 month, I have, my mind is grown and I am able to solve this problem easily, right? The blurriness drops, right, before the eyes. You have more clarity. Now you improve with these activities, and you can't avoid it. Like, I have seen, like, I usually give a lot of workshops and to colleges, to these training institutes, education firms, these, what we call them, ed tech companies, uh, and I have seen most of the people, they are not focusing on this quality, whenever you solve a problem, ask yourself, have you done, uh, actually, are you putting your effort, are you actually, have you actually solved that problem, or you just made fool of yourself? There is a difference between, solving a problem, doing some activity well, and second is just fooling yourself that I studied for 10 hours, I have studied for 4 hours. That's labor, that's labor work. And don't, don't do that, don't fool yourself, and don't do that labor work. You are not made to do that labor work. uh, वो कहते हैं ना कि यार, you just can't improve yourself, यार. You can't improve yourself by this labor work. You have to, uh, work. You have to work while being aware of whether you are actually doing something or not, and that feeling is inside you, you know that feeling is inside you. When you are actually growing, you become better at that thing which you are doing, your confidence increases. And don't fool yourself, don't live in any kind of bubble, face the reality, go through the process stepwise, and uh, you know go to the other side, win that particular activity whatever you're doing, so let's move ahead in the problem. That is, what we were doing. We were solving this problem. Now, how would you solve this problem? It's easy. This problem is very very easy, not that hard. Now I'll show you some algorithm, which we'll have to use in order to solve this problem. And the problem is, and that algorithm is, why I have thought of that algorithm. Just look at the constraints. Look at the constraints. The constraints, n is very very small, you know n is very very small, right? So what I can do here, instead of running Dijkstra for q queries, we have 10 to the power 5 queries, and one method is to run Dijkstra every time. So how many times you'll have to run the Dijkstra algorithm? You'll have to run the Dijkstra algorithm 10 to the power 5 times in the worst case, you know. So that is not a very good idea to execute. So what you can do instead is, since n is very very small, we must have some pre-processing algorithm. You remember when you can't calculate a prime numbers in a large range, we have some pre-processing technique. We call it sieve of Eratosthenes. We use some prefix sum technique, pre-processing techniques, binary lifting, right? These type of techniques, pre-processing techniques, we use so that the query processing becomes easy. So there has to be some pre-processing algorithm here, and if your mind gives you this intuition, then you are on the right track, my boy, right? So let's see what that algorithm is. That algorithm is Floyd algorithm. So you can go to this algorithm, that is Floyd Warshall algorithm. Study about it. This website is really one of my favorite websites to visit. One of my favorite websites, and it has the details here are really really nice, and they have written these blocks in really good detail, and all the mathematical interpretations with code snippets and everything, with the practice problems as well, right? So I'll recommend you to read Floyd Warshall algorithm in really detail from this website, and then you can also this is the implementation. That's all. I'll teach you how to do it, but it's easy. Now let's jump to the. We will use this formula. We will use this algorithm to solve this problem. So let's see how we do that. So in Floyd Warshall algorithm, we have k phases, kind of phases of you say upgradation, we can say. So initially we have the distance between each pair of nodes I and j stored in the DP array. So this contains the distance, the minimum distance between I and j, right? That's what this dpij contains, right? The minimum distance between node I and node j. Now what I would do is, what I'm gonna do is, I am simply initializing this dpij with the weights which has been given to us. So we have an adjacency matrix for the graph where adj ij contains the weight for the edge between I and j, right? For the edge between I and j, right? Now that's what I'm gonna initialize this DP array with. So for this particular graph, what will be this DP array? The DP array would be like this. So for 1 1 we have 0. For 1 2 we would have 5. For 1 3 we would have 9. For 1 4 we would have, again we have infinity, right? For 2 1 what do we have? For 2 1 5. For 2 2 0. For 2 3 we have 3. For 2 4 we have nothing, infinity. For 3 1 9. For 3 2 we have 3. For 3 3 we have 0, and then for 3 4 we have nothing, right? Infinity. They're disconnected, right? Now this is your DP array, right? This is your DP array that we have. Now what you're gonna do is you are going to update this DP array. You're going to update this DP array, and how? Let me explain that. Now the algorithm goes through k phases. So you iterate for k times. For I goes from 1 to k, and then for each I, that is the phase, or let's call it k, moves from 1 to n, k moves from n to n. So k is a phase number. So we have phase 1, we have phase 2, we have phase 3, like that. So for the first phase, what you do is you take k as the intermediate vertex, and you update all the nodes, you update all the edges through this kth vertex. Let me explain how. So you have a for loop here, j 1 to n. Now what you're gonna do is so there is an edge between I and j, and k is some intermediate vertex. So k is 1 initially, then k becomes 2, then it becomes 3, then 4, 5, 6, 7, like that. So what you're going to do is dp I and j. What does that represents? That represents the minimum distance between I and j. Now you calculate the distance through the vertex k. So how would you calculate it? It can be calculated like this. First find the distance from minimum distance from I to k, then from k to j. Now what I am saying, versus dp I j, the initial distance that we already have, and we take min of these two. That's the idea. So the idea is simple. I want to find the minimum cost from 1 to 3, or the shortest distance from 1 to 3. I'm gonna pick 2. I already have the distance between 1 and 3 as 9 in my DP array, and now I'm gonna pick 2, and I'm gonna say okay, let's go through 2. So what's the minimum distance between 1 and 2? It's 5. Now what's the minimum distance from 2 to 3? It's 3, and the sum is 5 plus 3. Is 5 plus 3 better than 9? Yes. 5 plus 3 is 8, while the direct edge has a weight of 9. So 5 plus 3 is better. So I'm gonna update my DP13 with 8. Initially it had 9. So that's what I'm doing here. Try to find a better route through the edge, through the vertex k, by moving through the vertex k. Right? Now choose k as 1, 2, 3, 4, all the vertex. Take k as an intermediate vertex. That's the idea for Floyd Warshall algorithm, and that's what I'm going to use here. Right? Am I right? So let's dry run it over this example. So when k is 1, I is 1, j is 1. I think the video is going to the code implementation part. Let's jump to the code implementation part, because then the video is going to get too much longer, and you will also get bored. So let's not do that. It's your job to take pen and paper and dry run this piece of code over this example, right? That's your homework. Okay. Now let's jump to the code implementation part of this problem. Let's read n, m, and q, the nodes, the edges, and the queries, and then let's create a DP array of dimensions n cross m, and initialize it with infinity. So here I have taken this INF to be a very large number, and then let's initialize dp of now this initialize it. So here I'm saying here I haven't added any edge, so let's add the edges. For 0, I less than m, I plus plus, a, b, c. So read A, B, read C. So dp of A, B would be what? It would be C, right? dp of B, A would also be C, right? And here dpii should be 0. So the self edge, there is no self edge. So for I less than equal to n, I plus plus, dpii would be 0. Now dpab would be C, dpba would be C. Now what we can do is, now here run Floyd Warshall process. Floyd Warshall process. So k phases, n phases, k is equals to 1, k less than equal to n, k plus plus, for I1, I less than equal to n, I plus plus, for j is equals to 1, j less than equal to n, j plus plus, dp of ij would be min of dpij comma dpik plus dpik j. For min, will that work? Okay, let's see. So here what you're going to do is, now process q queries. LR if dpLR is infinity, there is no route, print -1, else print the path. I hope I want Warshall. It should be A, right? Ik plus, this is also fine. Let's check and segmentation fault. Why I'm getting n plus 1, sorry, n plus 1, it should be of dimension n plus 1 into n plus 1. Okay, let's try running it. 558 minus 1 3, 558 minus 1 3. Let's try to submit it. I don't know why I'm getting errors over this problem. Maybe still wrong answer. Something is missing. Min of dpa b comma c, min of dp comma a comma c, dpk, no, ik is infinity, or dpk j is infinity. Continue. anything wrong do we have here? Not feel anything is wrong here. Infinite is okay, right? Got accepted, and that's cool. And I hope you learned something out of this problem, and I recommend you to submit this code by yourself. You can see how many submissions it took me. I don't know why it took me so many submissions for this simple problem, but yeah, sometimes your day is not that good, and you mess up in solving problems, and you also mess up in contests. Okay, so try solving this on your own, and I'll see you in the next one. Till then, take care. Bye bye, ladies and gentlemen.